In this lesson, we're going to add one twist to our work on 2D projectiles. And that is, we're going to look at 2D projectiles where the initial velocity is at an angle. So in the previous lesson we looked, or previously to now, we looked at situations where the initial velocity was horizontal. So the projectile was sort of released with an aim that's entirely in the X or horizontal direction. It wasn't released going up or down at all. That would have happened later as gravity acted on it. But here we're looking at projectiles that are released either pointed slightly upwards or pointed slightly downwards. And I want to introduce this by basically taking the exact problem we did last lesson and just making one tweak to it. So, in the last lesson, we had this scenario where there was a ball being thrown from a cliff. The ball was up here. And in the last lesson, the ball was thrown horizontally. So initially, for that first instant, it was moving only to the right. And then as time passed, gravity acted on it and caused it to curve down towards the ground. In this question, the change we're making is it's not thrown directly towards the right. It's thrown same initial velocity, but at an angle of 20 degrees above the horizontal. So that means the path this thing takes is going to look more like this. Okay, so my initial velocity, instead of being this way at 14 meters per second, is in this direction at 14 meters per second. Everything else I've kept the same about this problem. The building is 12 meters high. And the initial velocity, or the initial speed, is 14 meters per second. So we learned that a good way to solve these problems is to look at what's happening in the horizontal and vertical directions separately. So let's take that same approach here. So in each the horizontal and the vertical side, we have our usual variables, VF, VI, A, D, and T. And we spent last lesson going over a number of things that are going to basically be the same for every 2D projectiles problem. So one of the things we went over was that as soon as this thing is in the air, right before it's touched the ground and after it's been thrown, that whole period of time it's in the air, where the only force acting on it is gravity, which means its acceleration will be 9.8 meters per second squared down. So down tells me it's going to be in the vertical direction, and it's going to be negative. So we've got a negative 9.8 for my acceleration here. And because it's down and not right or left at all, the acceleration in the x direction is 0. There's no force pulling this thing left or right whatsoever. The only force is gravity, and it's going to pull it and accelerate it down. The other thing we said that because this is 0, it can't speed up or slow down in the x direction. So whatever its initial velocity is, its final velocity will be the same. And then the other thing we said was that the time was also going to be the same. Because time is not a vector, it can't really have x and y components. So that's going to be the same on both sides. Now, the last time we solved this problem, where it was at a horizontal initial velocity, we knew this was 0 because it wasn't moving up or down at all to start with. But here, we clearly have a little bit of upward movement at the beginning. So VI in the y direction is no longer 0. Also, last time we solved this problem, because this 14 was entirely in the x direction, we were able to just plug it in here for VI in the x direction. Again, now our 14 is not entirely x, so it can't go here. And it does have a little bit of a component in the y, so this is not 0. So those two things, our two VIs, are the things that are different now that this thing is being released at an angle. So how do I find the x and y components of this? Well, we're going to do a little bit of trigonometry here. So if I look at this 14 and I say, hey, that's a rather annoying vector to deal with. It's at an ugly angle. What I can always do with annoying vectors is I can split them into components. So I can replace this with an x component and a y component. And to find out what those are, I'll need to do a little bit of trigonometry. Remember, I know this angle here is 20 degrees. So let's do that. Let's do that trigonometry. I'm going to do it sort of down here on the bottom to give myself some space in the diagram to do some other stuff. So since I know this angle, I'm going to kind of center myself there for doing some SOHCAHTOA, which means this is my adjacent side, this is my opposite side, and there's my hypotenuse. So if I want to find x, I need to pick a trigonometry ratio that uses the adjacent side, so I can solve for it, and that uses the hypotenuse, so I can use that piece of information to help me solve for it. So adjacent and hypotenuse means I'm probably going to use cos. Then if I rearrange, I can solve for that x component. And I get 13.156 if I keep 5 sig figs. I can also do the same thing for this y component here. Again, if I center myself at this 20 degrees, y is the opposite side, and I want to use information about the hypotenuse. So opposite and hypotenuse means I'm going to be using sine. Rearranging gives me that. And I can solve for y to be 4.7883. So this is the length of this side here, the x component of my initial velocity. And this is the length of this component here, the y component of my initial velocity. So what that means is those numbers can go here for the x component of my initial velocity and here for the y component of my initial velocity. I'll put this in blue because remember the sort of template we were following last lesson is that all this stuff in green is what's going to be the same for every single problem, and the stuff in blue is going to be specific to this problem. So in this problem, I can say this guy is 13.156, and because VF and VI need to be the same, I can copy that up here. And on the y side, I've got 4.7883. Okay, so that is kind of the only new thing you need to know when we're dealing with a 2D projectiles problem where the initial velocity is at an angle. Again, the quick recap is that because we are not throwing this thing completely horizontally, we can't say that all of its speed is in the x direction here. And because it is going up and down at least a little bit, we can't say that this, in the y direction, VI, is 0. So instead of having a number we just chuck in here and a 0 we're putting here, we have to split this into components. Find the x part of the initial velocity. Find the y part of the initial velocity. And that's what goes here for initial velocity in the x and initial velocity in the y. After that point, the rest of the problem solving process is exactly the same as we would do before. You want to kind of decide which side you're going to start on. Remember that just knowing these three things here looks like a lot of information, but it's not enough to get you anywhere. You need to know D or T before you can do anything. And that once you find one of these T's, you can copy it over to the other side. Also remember that displacement can kind of throw people off sometimes. Remember, displacement is a straight arrow from start to finish. And because we need a displacement in the x direction and in the y direction, we remember that that arrow can have a y component and an x component. So we might sometimes write this as this is d in the x for the x component of displacement, and this is dy. I've got those backwards. This is dy for the y component of displacement, and this is dx for the x component of displacement. And so this is the guy that's going to go here, and this is what's going to go here. Okay, and that is all you need to know to solve problems on 2D projectiles. So, looking back at this problem, we are asked how long is the ball in the air for? Which means we want to find time. And we can find it on either side because they're going to get the same number either way. But since I only have these three things on this side, that's not a good place to start. So I'm going to have to start on the y side. Here I only know two things, but there's one thing we haven't yet written, and that is the displacement. This 12 meters is this here, which is the y component of displacement. So that goes here. And because it's going down, this is going to be negative 12. Remember, all these components need to have a direction, I didn't draw this one, but this guy's direction is down. So this guy has a length of 12 and it's going down, which is why we put a negative 12 here. So now I know three things over here. I should be able to start solving. This is a bit of a tricky one in that I think I can't solve. If I'm looking for an equation that has t but not vf, there's only one, and that's sort of my middle equation, but that one is really hard to solve for t in this case, unless you know and want to use the quadratic formula, which you don't. So what we're probably going to do here is solve for vf first, and then solve for t after that. I'll leave you guys to do that. But hopefully this lesson has served as a good sort of intro on how to deal with an initial velocity that is not horizontal, but is at an angle.